All right, so I wanted to do an additional example where we use the work energy theorem. I understand that it ends up looking a lot like conservation of energy, and then you would think, like, why should I even care? But I also think that it's, important for us to be flexible in the methods that we use. And so we're going to look at this particular problem and we're going to solve it using the work energy theorem. So here's the scenario. We have this piece of pipe, and it basically, in the area that we're concerned with, it's like a quarter circle with a radius of 0.4 meters. There's actually this collar. It has a mass of 4 kilograms, and it goes around this pipe, but it's attached at this location right here by a spring. And so as the collar moves, it's really going to be influenced by both the force of the spring, but it's also going to be influenced by gravity. So there are two forces that we're working with here. Now, the 2 points that we're interested in looking at the motion of the collar, it's going to start up at point A and it's going to go down to point B. And our job is to try to figure out how fast is it moving when it gets to point B. Now, there's a couple other things that we need to know. We actually are given the velocity when it's up here at point A, and you can see that the distance from the attachment to where it would be at point A would be 0.1 meters. So that would be the length of the spring when it's at point A. The reason that I'm bringing this up is we are also told that the unstretched length of the spring is 0.2 meters. And so that means that when the collar is at point A, our spring is actually compressed a certain distance. Now, if we imagine when the spring of the collar is right here, of course the spring would go from here to here. And so what we could figure out is we want to know the length here, and we'll talk about that in a minute. But so this is where we can sort of, like, knowing all these things is going to help us put it all together. So the work energy theorem is going to say that the kinetic energy that I start off with, which would be the kinetic energy at point A, plus the work done in going from A to B, is going to be equal to the kinetic energy at point B. Now, for point A, I know the mass of the collar and I know its velocity. Now, there are going to be two different forces that do work as I go from A to B. And so I'm going to say the work from A to B done by the spring plus the work going from A to B done by gravity. And that's equal to 1/2 the mass times the velocity at B squared. So, what is the work done by the spring? Now, we learned about the work expressions for the work done by a spring and by gravity. And so I'm going to write them in a more general way and then put in specific values. So the work done by the spring going from A to B is minus 1/2 k times the x that it would have at B squared plus 1/2 k the x at A squared. Essentially, it's actually minus the 1/2 k x final squared plus 1/2 k x initial squared. And in this problem, I've just substituted A and B. For the work done by gravity, we have minus mg yb minus ya. And you can see this would have a really similar expression. It would be minus mg y final plus mg y initial. And this is going to be all equal to 1/2 mv b squared. Now let's put some values in for these numbers. The mass of the collar is 4 kilograms. Its velocity was 2 meters per second when it was at point A. Then I have the spring constant. I didn't mention it, but I did write it down over here, was 400. Now, when I want to figure out the length of the spring when we're at point B, what I did is I noticed that this distance right here is going to be 0.4, and this distance right here is going to be 0.3 because of that suspension is 0.1 from the top, and this whole part is like a quarter circle. So the entire distance would be 0.4. And then I noticed that what I have is like equivalent of a 3, 4, 5 triangle, so I know that this distance here is going to be 0.5. That's the total length of the spring. However, that's not going to be the x that I would put in here. The x would be the natural length minus the length that it has. And so this would be 0.5 minus 0.2, that quantity squared, and then plus 1/2 k, and then this would be 0.1 minus 0.2 squared. This is the one case where I just was telling people to be super careful about signs, but the natural length is 0.2, and the length that it had here was 0.1, so it's technically compressed, so our x is negative, but we square it, so it ends up not mattering. And this is all equal to 1/2 times 4 times the velocity of v squared. And so this ends up to be 1/2 times 4 times 2 squared minus 1/2 times 400 times 0.3 squared plus 1/2 400 times 0.1 squared equals 1/2 4 VB squared. And so I just get out of the way. It's 1/2. I know some of the numbers aren't coming out that good, but hopefully you can see it. In the end, we end up with, this term is 8, this is minus 2, this next term is 18, and then 15.69 is equal to 2VB squared. So this is just, if you want to check your math along the way. And our final speed at B ends up to be 4.45 meters per second. And so like I said, I think it's good to be able to think about, when I have these forces, how do I express the work that they do, and put that together with the relationship of that work to the kinetic energy. Like I said, it is also a problem we could do with conservation of energy, but it still is a good thing to have a more complete understanding to be able to use this approach as well.